Hi, I'm Mike Stanzik and welcome to Digital Electronics Classroom. Thanks for joining us today. We will be talking about universal NOR gates. Now the last video was about universal NAND gates, and in that we went through the logic of how we came up with universal NAND gates to take the place of AND or inverter gates. I'm not going to go into as much detail for the NOR gates, so I highly recommend that you watch the previous video before you watch this one. So let's get started. Universal NOR gates, or just NOR gates, they're just universal. Okay, and so let's take a look at what a NOR gate is. So if we have an OR gate, and then we add an inverter after it, this is what we're achieving when we make a NOR gate. So we have X or Y, and then the whole thing is inverted like that. So you can see that this is a term that's in a product of sums format. Instead of being an AND here, we have an OR. And so this is achieved, and there's a gate designed for this to do in one gate operation, if you will, which would be this one here. And this is what we call a NOR gate. So we have an OR and then a NOT afterwards, so it's a NOR. So we have an OR inverter configuration. Okay, the truth table for the NOR gate looks like this. All right, 0, 1, 0, 1, 0, 0, 1, 1 for our input sequence. And let's just make this the OR and then the NOR. So in the OR, we have everything is a 1 except for that first row. And in the NOR, everything is 0 except for that first row. So that's the truth table for the NOR gate. We're not going to look too specifically at the table for the NOR gate. We're going to more deal with the circuit diagram and look at transformations between the AND, the OR, and the inverter to the NOR gates and having that same functionality with them. Okay. So let's go ahead and take a look at those transformations. Well, one thing to be said is that you're going to use NOR, universal NOR gates, when you're dealing with product of sums situations, product of sums expressions. And so when we write our expression here from our Carnot map for our problem, we're going to write it in max terms form. If you're going to do min terms, then you would use NAND universal gates. Okay, so the transformations. Inverter. So to make an inverter for out of a NOR gate, you simply take the input and feed it into both inputs of the NOR gate. So if here's X, then you would get X bar out. Now this is what I'm talking about and not going into as much detail into why this works. So if you're interested, go ahead and look at the NAND video. OR gate. I think this one's pretty straightforward to see. You put it into the NOR gate, but the NOR gate inverted it on the output. And so we need to invert it back to an OR. And so we use the NOR gate configuration that inverts and then invert it back to an OR. And so we have X and Y coming in. This is X or Y bar, and then this is just X or Y. And then we have the AND. And the AND gate, to achieve the AND gate, we need a NOR gate on the end. And then we need inverting of the inputs. So we're going to invert these inputs with the NOR inverter configuration, X and Y right there. And so this will end up with X and Y as our output. So these are our three transformations, and so we're going to use these transformations to create an all NOR network. Okay. So just to repeat, we got a inverter is the inputs are put into both of the inputs. The one input is put into both of the inputs of the NOR, and we get an inversion. For an OR gate, we take both inputs into one NOR, and then we put an inverter afterwards to invert it back to an OR. And then on an AND, we invert both of the inputs X and Y, and so they come in as X bar and Y bar here. And then if we put that into a NOR gate, you get X and Y. You can figure that out with De Morgan's if you're looking for a hint. Okay, so let's do an example here. So I'm going to build up this truth table for us, and it's going to look like this: 0, 0, 0, 0, 0, 1, 1, 0. And so this will give us our Carnot map. That looks like 0, 0, skip, 0, 0, 0, 1, skip, 1, 0. Okay, so we're looking at max terms here. So we're going to identify the max terms by circling zeros. And so we have a nice set of 4 zeros across this top row. And then we have 2 sets of 2 zeros that come down like that. Looks like little animals, like a little turtle or something. So let's go ahead and write out these max terms now. So let's look at the top row. Well, we'll write it as min terms first. That's how we do this. And so if this were ones, how would we write the min term? And this would just be X bar. Or this one here would be Y and Z are both 0. So this would be Y bar, Z bar. Or this one, Y and Z are both 1. So YZ. So that would be the min term of the complement, we would say, because that's where these would all be ones. So now we're going to do a complement on each of these to get the max term form for this particular K-map. So the complement of X bar is just X. The complement of Y Z bar is going to be change the sign and change the operator. So this is Y or Z. And then same thing for YZ would be Y bar or Z bar. Okay, so this is our expression. And actually I'm going to copy it down right here. F equals X, Y or Z, Y bar or Z bar. So I can scroll the screen up and we can look at where we go from here. Perfect. Okay. So we have a couple of bullet points about what we're going to do next. And so the first one is that we solve the K-map for max terms, which we already did. And the second one is we're going to build the AOI, so AND or inverter circuit. We're going to transform to NORs, and then we're going to simplify if we can. All right, so let's go ahead and start out with the AOI circuit. So we got X and Y or Z and Y naught or Z naught. And so this is going to take the POS form where we're going to end with an AND. And we're going to need an OR here. And this one's just going to be X. And this one's Y or Z. And then we need another OR. That's going to be inverted Y and inverted Z. So Y, Z. Okay, so that's the AOI form. We have X and Y or Z and Y naught or Z naught. Okay, and so we check this one off, check that one off. Next step is to transform to NORs. All right, so now we're going to substitute in for the NORs that we looked at in the transformation section that we looked at last. So I'm going to start here with the AND. So the AND gate is a NOR with 2 inverter NORs leading into, oops, actually let me leave some space. Oh, no, that's good. Okay, sorry. All right, so this is an inverter NOR, and that goes to X. And then we have an inverter NOR. And we have a third inverter NOR. Like that, okay? So that's our AND section. Now we have the ORs. Remember, the OR is a NOR with an inverter NOR in front of it. So we're going to have a NOR with an inverter NOR. And then a NOR with an inverter NOR. So this is our OR section. And then we need to invert on this bottom one the Y and the Z path. So I need two inverters. There's an inverter. And there's an inverter. There we go. So now I have Y and Y bar. And we have Z and Z bar. Okay, so there we have it. That's the this is the transformed to NOR version of this. And so the last step we have to do is simplify. And so we're going to simplify by looking for double inversions. And so we can see that right here, we have two inverters in a row, and the same thing with right here. Now, I knew to look for them here because they're going to show up if you do this POS formation with NORs. That's why we use the NORs with the POS, is because we get to simplify this section right here, and it works out nicely. Okay, so that's what I'm looking for, and everywhere else nothing simplifies, so that's what we end up with. So let's redraw the circuit one last time, and we'll take out these double inversions. So we're going to end up with a 3-input NOR, and it's going to have a NOR inverter coming from X. And then we don't have to draw these double inversions there, so this would just be a NOR. And that comes from Y and Z. Okay, and then we have another NOR. This one does need inverters on the inputs. With the NOR configured inverters. And we got Y going to this one, and Z going to that one. And so this is our final circuit. So we can see that we have 6 NOR gates. They're all NORs, and that affects the same as the original AOI, which had 3 different types of gates. And like we talked about in the NAND video, 3 different types of gates necessitates 3 separate chips, and having 4 gates on a chip for 2 input gates, we could do the NOR version with 2 chips. So we reduce the number of chips, and thus we reduce the cost. We also reduce the diversity of the gates, so we're dealing with just the NOR gates, which has some advantage as well. Okay, that's it. I hope you enjoyed it. I hope you got some value from this. Again, if you have any questions, please leave them in the comments. I'll be happy to respond to you, or if it prompts another video, we'll make another video. As always, I appreciate you being here. Please subscribe to the channel. Please like the videos. My name is Mike Stanzik, and this is Digital Electronics Classroom. And until next time, have an amazing day.